In the very beginning, there was no sky to gaze upon, no stars, and no space to hold them. There was a silence so dense it had no name. Then, an ignition. Time began to flow, and from that first breath of the universe came the simplest ingredients, hydrogen and helium. Much later, the first massive stars ignited. They burned brief and fierce, and deep inside their cores they forged new elements: carbon, oxygen, silicon, and iron. When those stars died, they exploded, scattering those heavy ashes across the void. One of those cold clouds of stellar ash hung in space until something disturbed it, likely a shockwave from another dying star. The cloud collapsed inward, and at its center, our young sun caught fire. Around that newborn sun, a flat disk of dust and fragments began to swirl. Grains collided, sticking together through weak forces. They formed pebbles, then rocks. As these clumps grew, their increasing gravity pulled in more material, a runaway avalanche effect that eventually built a massive protoplanet. Inside this early glowing protoplanet, the immense heat of impacts caused heavy materials like iron and nickel to sink toward the center, forming a dense metallic core. Lighter rocks floated up, forming a molten crust. This early Earth was a toxic, molten wasteland, completely hostile to life. Yet these exact violent mechanisms locked in the structural foundations needed to protect a future world. Then came a crash that cut through the darkness. A young Mars-sized planet we call Theia slammed into the Earth. It was an oblique, glancing blow that ripped material from the surface and launched an arc of incandescent debris into orbit. Earth's gravity quickly pulled that glowing debris together. In a matter of weeks or months, it compacted into a single, massive body, sitting much closer to Earth than it does today: the Moon. Without a moon, the globe on the left wobbles chaotically on its axis. But with a massive lunar neighbor, the immense gravity acts like a metronome, slowing Earth's frantic rotation and locking its tilt into a steady rhythm. Without that violently created neighbor, the seasons would have swung rapidly from extreme heat to deep freeze. The Moon provided the rhythmic stability required for any future climate to settle. The surface remained an ocean of magma, covered by a heavy atmosphere of steam and carbon dioxide. As the heat slowly radiated away into space, the water vapor condensed. Rain fell on hot rock, evaporated, and fell again for millions of years, until the water finally pooled into permanent oceans. This set up a slow, natural thermostat. When the planet warms, rain dissolves surface rock and flushes carbon dioxide down into the deep ocean. This process regulates the surface temperature over deep geologic time. Along the young coasts and deep underwater vents, the Moon's close gravitational pull dragged the oceans back and forth. Tides crashed and receded, repeatedly mixing minerals and heat in a constant cycle of wet and dry. This abstract model shows a microscopic, semi-permeable droplet. Tidal stress forced internal molecules to interact and recombine. Eventually, a sequence accidentally copied itself with slight errors. Weaker copies dissolved, but stronger ones survived the endless cycles and multiplied. Trillions of these chemical attempts happened across deep time, driven by the rhythmic energy of the tides and heat. Matter was slowly learning to hold on to energy and remember its own shape. Some of these early cells found a way to use sunlight to convert water and carbon dioxide into energy. This process released a highly reactive waste product, oxygen. At first, this toxic oxygen oxidized the iron dissolved in the seas, sending heavy layers of rust to the seafloor. Once the ocean could absorb no more, oxygen saturated the air, eventually forming an ozone layer high above that shielded the surface from brutal solar radiation. Oxygen provided an enormous new source of energy for the cells that adapted to use it. With more power, biology scaled up. Larger cells actively engulfed smaller ones, absorbing them. The host protected, the guest generated power, and they merged into complex multitasking organisms. Passive filtering was no longer the only way to survive. Some organisms began hunting and feeding directly on others to steal their energy. This triggered a massive evolutionary arms race. Hunters evolved stronger muscles to swim faster, and their primitive light-sensing spots curved into lenses to track prey. The hunted grew hard shells, developed sharp spines, and camouflage to stay alive. The constant threat of predation, rather than peaceful harmony, pushed biology to its limits. It forced an incredible explosion of diverse shapes, senses, and survival strategies throughout the ocean. Along the shallow coastlines, the push and pull of the tides created a harsh testing ground. When the water receded, aquatic creatures were left exposed to the open air, forced to survive until the surf returned. In this skeletal evolution of a fish's fin, we see how desperate environmental pressures drove physical changes. Fins slowly thickened into load-bearing limbs, with joints and digits to push against the mud. Internal air sacs adapted into primitive lungs to drink in the oxygen-rich air. The final barrier was reproduction. Eggs laid on land quickly dried out. The solution was a biological casing, a protective external shell holding an internal cradle of fluid. Animals could now be born far from the tide pools. The transition to solid ground took millions of painful, incremental steps. Slowly, the hostile boundary line between water and land became a wide open road. Today, the Earth rests in a delicate, moving equilibrium. Fire burns below, solid rock sits in the middle, and liquid water flows above. The endless recycling of the crust and the atmosphere maintains a steady balance. The entire history of the planet reveals a simple recipe for existence: a protective physical boundary, a steady flow of energy, and a continuous system of copying instructions with small, useful errors. Everything we interact with today is the direct result of that unbroken, violent chain reaction. We are built from the ashes of dead stars, in the chemical memory of ancient oceans. Science can trace the mechanics of these events back to that first cosmic ignition. But the underlying mystery of why these exact physical laws govern the universe remains the greatest frontier of human discovery.